Okay, I do have some homeworks to pass back. Those of you who aren't here in person, obviously the next time you're in class, you can pick up your homework. Jordan? Okay. Logan? Let's see. Jake? Julia? So everybody, everybody did okay. There were just two things where people consistently had, there were two things where people consistently had problems. On problem one, when you do that, the stress vector is equal to the stress tensor times the normal vector. The normal vector is the unit vector in the direction of the normal. So you had to take that vector as given and convert it to the equivalent normal vector and then do the multiplication. And then, let's see. The other thing that people had issues with, and oh, let's see. And so I just, I'll give myself a blank slide on top. So, yeah, so for problem one, you had to take that normal vector and take that, the magnitude of the normal vector is equal to the square root of, oh, and by the way, I did make a typo in the solution for this problem, but I did post a corrected solution online. So it's available under the homework solutions. You'll see homework one solutions revised. But anyway, it's supposed to be 1 squared plus 4 squared plus 8 squared. So you add, in the case of square root, that's equal to 9. So the normal vector you should have used was 1 over 9 I plus 4 9 j plus 8 9 k, and that multiplication, and then that's what you should have done. Then the other thing where number for C, where you're given the straight tensor, what you needed to do was to say that, epsilon 1 was equal to 36 times 10 to the negative 6. Epsilon 2 is equal to 12 times 10 to the negative 6. Whoops, I'm sorry, 40. Epsilon 2. Epsilon 3 is equal to 30 times 10 to the negative 6. Epsilon 2 is equal to 40 times 10 to the negative 6. Epsilon 3 equals to 0. Epsilon 3 equals 25 times 10 to the negative 6. And because the epsilon 3 was not equal to 0, you can't say it was plane stress. So what you needed to do was you needed to put this in the strains in the column vector form. 1 2 epsilon 2 3 epsilon 1 3, and then set that equal to your, so your stress was equal to your compliance matrix times your strains in this vector format. And the other thing was that, and then the other thing that several of you have problems with is that in problem 5, when you have the K is equal to sigma times the square root of pi times A. This A is the half crack length by the convention that we were given, because the way we defined it, if you had this infinite crack, we defined this total crack length as 2A. So you had to take this A that you solved for and multiply it by 2 to get the 2A. But, I mean, hey, look, overall, you did okay. I'm not worried about anything. So any questions about this? Okay, then a few more administrative things. Something you'll be interested in is your midterm, in that basically I'm setting the midterm for this class to be 2 weeks from today, on October 24th, and it'll cover the material in homework 1 that you just got back and homework 2 that's due next week. And that's what you'll be responsible for the midterm. Midterm will be an hour and a half next week. So just, it's a 2.5-hour class period, but I'm not going to give you a 2.5-hour midterm. So it'll be an hour and a half, and I'll have more details about the midterm next week. Just note that, just so you know, the midterms are open book, open note. So, and particularly for some of these tables to make life easier, if you're going to need to pull things from these various tables, I'll reproduce the tables so you don't have to desperately look through your notes to find some of these very long tables. But it's open book, open note, closed computer. I don't want you to be able to look up the answers on the internet while you're taking the exam. But anyway, the midterm for this class will be on October 24th, which means for those of you, I'll talk about on Thursday, but for those of you who are also taking my finite element class on Thursdays, it'll mean that midterm will be on Thursday, November 2nd. Not making you do two. For those of you who are taking both of my classes, not making you do two midterms in 1 week. So anyway, if any of you, so the midterm for this class will be 2 weeks from today, October 24th. If anybody has any real problems with that date, let me know, and we'll see what we can do. So speaking of homework 2, does anybody have any burning questions about homework 2? Realize I've been doing this long enough to know that I'll be lucky if a lot of you have even started looking at homework 2. But anyway, if you have any questions over the next week while you're working on it, please be sure to let me know. And like I said, there'll be more details on the midterm next week, but like I said, it'll be hour and a half, open book, open note. So any other questions about administrative stuff for the moment? Okay, if not, and anything we covered last week, last week was including homework 2, but anything we cover today and anything we cover next week will not be covered on the midterm. Just what we covered through last week, which was included in homework 2, that's what you'll be responsible for the midterm. So in any case, we're chugging down the road of linear elastic fracture mechanics, and by the end of today, we'll actually start talking a little bit about what happens if you start allowing for some plasticity. but so we're starting to move away a little bit from the world of everything being totally linear elastic. And then next week, so either in the middle or end of next week's lecture, I anticipate reaching the end of the material on linear elastic fracture mechanics. So either we'll start right before the midterm, or depending on how long it takes, right after the midterm, we'll be starting on the idea of elastic plastic fracture mechanics, which is important because metals do yield and have a plastic response. But for the moment, at least for the first part of today's lecture, going back to linear elastic fracture mechanics, we've so far talked about two parameters that describe the behavior of cracks. So we've talked about the energy release rate, and we've talked about the stress intensity factor. And the strain energy release rate quantifies the net change in potential energy that accompanies an increment of crack extension. And the stress intensity factor characterizes the stresses, strains, and displacements near the crack tip. Now, the energy release rate describes the global behavior, while the stress intensity factor is a local parameter. But for the case of linear elastic materials, K and G are uniquely related. So here's our old friend, the through crack in an infinite plate subject to uniform tensile stress. And just highlighting, by these definitions, the crack length is 2A for this case, just to hit home this point one more time. We define the strain energy release rate as being pi times sigma squared times 1/2 the crack length divided by the modulus. And we define the stress intensity factors equal to the stress times the square root of pi times A. Well, we look at this and we look at this, and you just do a little bit of almost trivial algebra. Basically, you take this, you square it, you'll have the square root, the stress squared times pi a, and you divide it by the modulus. It's almost trivial algebra to say that the strain energy release rate is equal to the square of the stress intensity factor divided by the modulus. But this is only true for linear elastic materials. Now, there's a little bit of a condition. These expressions here that we talked about are all for the case of plane stress. If we look at the case of plane strain, we have to replace E in these expressions times the modulus over 1 minus nu squared. So what we're going to do is, in general, when we talk about the modulus, what it's going to be is we're going to refer to it as this parameter E prime. And it's just so we always don't have to rewrite everything. What we're going to say is for the case of plane stress, E prime will just be equal to regular old Young's modulus. And for plane strain, we're going to say that E prime is equal to E divided by 1 minus Poisson's ratio squared. So we're going to write these equations. So we'll formally write the equation, say that the strain energy release rate is equal to the square of the stress intensity factor divided by this E prime material property, where this way it'll make it a general case. So for the case of plane stress, this E prime is just the modulus. For the case of plane strain, you also have to throw in that term related to the Poisson ratio. Okay. Now, one other thing we have to do is these equations we just talked about over the last couple of minutes, we only defined it for this special case of a through crack in an infinite plate subjected to straight, regular tensile loading. So we've not proven that this relationship is a general relationship that applies to all configurations. So we're actually going to go through an exercise to show that this actually is a general relationship that's true whether we have an edge crack or the other various and sundry conditions that we talked about. And Irwin performed an analysis that provides, to an extent, the needed proof. And we're not going to dot every I, cross every T in the proof. We're just going to go over in a general sense, what the proof is. So what we're going to do is we're going to define a crack of initial length A plus delta A. So that's represented here. So we'll arbitrarily define this origin here in the middle of the crack, and we'll say the distance from half the crack length to this origin is A, and then from the origin to the end of the crack is delta A. And it's just convenient in this case to place the origin of distance delta A behind the crack tip. And we're assuming the plate has unit thickness. And now what we're going to do between this origin point and the end of our original crack, we're going to apply a set of compressive stresses to the crack faces between x equals 0 and x equals delta A. And these stresses are going to be big enough that now we're shown in this figure here, we're going to close the crack. And we have the magnitude of the crack, it's somewhat of a non-variable stress. And the idea also of this sloped curve is to represent the work required to close the crack. Obviously, right at the edge of the crack, it's going to take less work to close the crack than it is. You get farther in, the cracks, you have a bigger displacement because this UY here represents the displacement from the plane. You're going to need more work to close the crack. So figure that this is a plot of the work required to close this crack from x equals 0 to x equals delta A. So, and we're going to be bouncing around. So talk about that. So what we're going to say is we're going to say that our strain energy release rate is equal to the limit as this delta A goes to 0 of the change in strain energy divided by the extension of the crack length for a fixed load. And that's getting back to the idea that when we talk strain energy release rate, it's not per unit time like you normally think of in terms of rate. It's in terms of unit distance. So this delta U here is the work of crack closure. So what we have is, imagine these are increments of work. So it's the sum of all of these increments of work from x equals 0 to x equals delta A. And we have to sum all of these little increments in our change of work. And we're starting in our baseline, and all we go up the curve, we have these additional little increments in work. So what we have then is that this delta U here is equal to the from x equals 0, x equals delta A of our increments of strain energy as a function of x. And this increment of strain energy is equal to 1/2 times the force at x multiplied by the displacement of x. And since it's the area under the force displacement curve, imagine that this is a force displacement curve. So each of our little increments is a triangle. So it's the addition of the force, the force times the distance divided by 2 because it's a triangle, and it's a triangle, and we're summing up all these things. And the other thing, because we have two crack faces, we have a top crack face and a bottom crack face, we have to multiply it by 2. So the 2 will cancel out with the 1/2. And the other thing we can do is remember from strength of materials, a force is equal to a stress times an area. So we can say this Fy of x is equal to our stress for our current value of x multiplied by our displacement, multiplied by the thickness, but it's just a unit thickness. So that takes care of that. Oops. Yeah. So. Okay, our distance is our stress times dx. That's our x direction. So we have the force, but the force is equal to the stress times dx, and that's our x dimension of our area. The force is equal to the stress times the area, and that's where unit thickness, it's dx along the x direction, 1 into the plane of the paper, and this uy is what we had before. So we now have our increment in strain energy is equal to the stress times the displacement multiplied by our increment of distance dx. Okay. Now, for this use of y, what we can do is we can go to our table for the case of mode 1 loading, and we look at uy, and we say for theta equals pi. Well, that means theta over 2 is equal to pi over 2. And we say theta equals pi because if we defined our origin here, to get behind the crack, we go 180 degrees from the origin till we get to where the crack is still open. But if we look here, if theta is equal to pi, that means pi over 2. So cosine of pi over 2, cosine of 90 degrees is 0. So that eliminates this whole term. Sine of pi over 2 is 1. So that just takes this term and sets it equal to 1. So when we do all of that, what we have left is our displacement in the y direction is equal to, and rearranging things just a little bit, kappa plus 1 times our stress intensity factor measured at the original crack tip, A plus delta A. So we're talking the stress intensity factor at the original crack tip before we applied any of these closing stresses, divided by 2 times mu, which is the shear modulus. And for this term here, our r over 2 pi, when we look at our distance from the origin, our distance from the origin is equal to delta A minus x is the distance from wherever we are to the end of our original crack tip. So, yeah, there we go. So what we have is then, so for the dimension term, which was r square root of r over 2 pi, it's delta A minus x. So it's the distance from our current value of x to the end of the original crack tip, and then divided by 2 pi. Okay. And for our shortened crack, we know that if we go back, I didn't reproduce it, but if we go back to those tables we have for the stresses for mode 1, that our normal stress required to close the crack is equal to our stress intensity factor for our shortened crack divided by the square root of 2 pi x. So this is our, right. So this is our stress intensity factor for the distance equivalent to our shortened crack. So when we take all of these equations and combine them together and do lots of algebra that I'm going to spare you, we get that our strain energy release rate is equal to the limit as delta A goes to 0 of kappa plus 1 times the stress intensity factor at A, the stress intensity factor at A plus delta A divided by 4 pi mu delta A times the integral of 0 to delta A of square root of delta A minus x over x, all this integrated over dx, and we go through and we do the integration and we do lots of algebra, which I'm going to spare you. We end up with kappa plus 1 times stress intensity factor squared divided by 8 mu, which we can say is equal to the stress intensity factor squared divided by this generic E prime term, and we make it the generic term because this kappa term is a function of our loading conditions. So it counts the fact of whether it's plane stress, plane strain, various geometries, or whatever. But the point is it's kind of an esoteric analysis, but we ended up with that same expression we got for the originally for the relationship between the strain energy release rate and the stress intensity factor, so we can make a reasonable claim that this expression is true not just for the case of an infinitely long plate with a through crack. And you can go through the same type of analysis for other types of loading. So if you do mode 2, you do the transverse shear stress and the displacement in the x direction, and the in-plane shear stress, because it's x, y, and the displacement in the x direction. For mode 3, it's the transverse shear stress and the out-of-plane displacement. So you can do the similar type of analyses for all three of the loading modes, And when all three modes of loading are present, you can say that the strain energy release rate by the principles of superposition, you can say that it's K1 squared over E prime plus K2 squared over E prime plus K3 squared divided by 2 mu. And because energy release rate, like energy, it's a scalar quantity and everything's linear here, so that's what allows us to apply the principles of linear superposition. Now, the thing to keep in mind, like anything relating to approximate simplified analyses, there are a couple of things to keep in mind. First of all, this equation assumes self-similar crack growth, that if you have a planar crack, it stays planar no matter what you do to it. It may change its size, but it maintains a constant shape as it grows. So this equation works great if your situations follow this follow this simplified situation. Now, given the fact that and many times things don't follow these simplified situations, this expression is not necessarily universally true. Not universally true. So in real life, mixed mode fracture is somewhat more complicated, and next week we'll give a bit more sophisticated analysis for how to compute the energy release rate for the case of mixed mode fracture. So, any questions? Okay, so what we're going to do now is we're going to start very subtle, very cautiously extending our considerations to the world where things aren't just totally linear, aren't just totally linear elastic. So as we talked about, I believe last week, linear elastic stress analysis of sharp cracks, when you do that, we talked about the fact that because you have that radius in the diameter, you predict infinite stresses at the crack tip because you have that radius in the diameter. When your radius goes to zero, obviously you can't divide by zero, so it goes to infinity. But real materials, having never studied mechanics or physics, have finite stresses at the crack tip. First of all, because in real materials, the crack tip radius must be finite. You can't have an infinitely sharp crack in real life. We talked about that at the very least, it's related to the atomic radius. And another very common limitation is that inelastic, a lot of times, particularly because you're concentrating, as we've talked about, you concentrate the stresses at the crack tip, you can locally go above your yield stress, which means that you'll have inelastic material deformation, such as plasticity in metals or crazing in polymers, and that leads to further relaxation of the crack tip stresses. So the elastic stress analysis, as the crack tip grows and your plastic zone gets bigger, your elastic stress analysis becomes less and less accurate. Now, here we're going to talk about some simple corrections to linear elastic fracture mechanics that are available when moderate crack tip yielding occurs. Moderate obviously being a judgment call. Now, for more extensive yielding, when you start getting not so moderate amounts of plasticity, you have to apply alternative crack tip parameters that take nonlinear material behavior into account. And we'll start talking about that when we talk about elastic plastic fracture mechanics, that will be in the not horribly distant future. So there's two relatively simplified approaches that have been developed to estimate the size of the crack tip yielding zone. The Irwin parameter, which we'll talk about first, in which it uses elastic stress analysis to estimate the size of the plastic zone, and another method called the strip yield model. And both approaches lead to simple corrections for crack tip yielding. Now, when we talk about the plastic zone, when you think of plastic zone, it applies just to metals. but just to note that people have applied these techniques to other types of material systems, polymer, ceramics, etc., which don't meet the definitions of plasticity in the classical sense that you think of when you think of metals. Okay. So the first approach we're going to look at is the Irwin approach. So on the cracked plane where theta is equal 0, again, if we go back to our simple tables, we can say that for linear elastic material, the stress in the x direction is equal to the stress in the y direction is equal to the mode 1 stress intensity factor divided by 2 times pi times the radius. So as a first approximation, what we're going to do is we're going to say that the boundary between elastic and plastic behavior occurs when these stresses satisfy a yield condition. And we're going to look at simple plane stress conditions. So we're going to say that when our y direction stress is equal to our yield stress in the material, we're just going to use that as our simple, our maximum stress criteria to say this is when our stress in the y direction equals the uniaxial yield strength of the material, we're going to say that that specifies the boundary between the elastic and the plastic zone. So if we take this stress, replace it with the yield stress, and do just a little bit of almost trivial algebra, we get that the radius of our plastic zone is equal to 1 over 2 pi times our stress intensity factor over our uniaxial yield stress squared. So a graphical representation of this. Now, if we neglect strain hardening, and what that means is if you're looking just at your stress strain curve, we assume that once you hit your yield stress, your material is just perfectly plastic. It's just no matter how much additional strain you put in, it just stays at the constant stress. And that's different from, and we're going to refer to this. So this is no strain hardening. In the case of strain hardening, you get a reduced slope, but you do get a continued increase in stresses for strains with increasing strain even once you yield. So for the case of perfect plasticity, what we say is if you look at this dotted line as the initial approximation, that you get your increases of stresses as you get closer to the crack tip, but once you hit the yield stress, that's it. And your stress then just remains flat all the way to the crack tip. And that's this Ry term that we just applied. So the stress singularity is truncated by yielding at the crack tip. But this simple analysis is not strictly correct because it was based on an elastic crack tip solution. We assumed that everything behaved perfectly until it got here, and then you just arbitrarily truncated things. Now, in real life, once you get yielding, things could be perfectly elastic, but your stresses have to redistribute in order to satisfy equilibrium. This cross-hatched reason here, this is all forces and stresses that would be present in an elastic material, but because we've yielded, they aren't there. Now, this initial analysis we did assume that these forces just disappear. But in order to maintain equilibrium, we can't just say that these forces magically disappear. They have to be redistributed within our stress displacement curve. We have to redistribute the stresses within the rest of this zone. So what we do is we have to we have to say that the plastic zone size is actually bigger because we have to take those stresses and redistribute them so that if we do an area under the curve, we get the same results for our area under the curve. So we have to take these stresses and use it to and account for their effects by expanding this plastic zone size. So we're basically, all this little area here is basically taking these stresses and redistributing them here, and therefore we still truncate at the yield stress, but the length over which we truncate the yield stress is bigger than for the purely elastic material, because we can't carry these, because once you get above the yield stress, you can't increase the stresses. So if you do a quote unquote simple force balance, again, simple always being the relative term, we can say that and make sure, did I make any notes? No. So we can say that our product of our yield stress times the plastic zone size. So basically this, this area in here is equal to the integral from 0 to our original radius of our stresses times dr, which is the integral from the 0 to our original radius of k1 divided by the square root of 2 pi r. We define it as the stress, dr, the integral of the radius. So if we take this and we integrate it, and we can take the k1 over the square root of 2 pi out. It's just 1 over the square root of r, and 1 over the square root of r dr, and we carry out that integral. And so what we end up getting is that the radius of our plastic zone is equal to 1 over pi times k1 divided by the yield stress squared. And so if we compare this to Ry, so if we compare this to Ry, we said that Ry is equal to 1 over 2 pi times K1 divided by yield stress squared. So, it's pretty obvious saying that Rp is twice as large as Ry, our first order estimate. Okay. So if we go back to our figure here, other thing we can say is that the material in the plastic zone, because the material in the plastic zone carries less stress than it would if the material remained elastic, because we truncated everything at the yield stress. So Irwin accounted for this softer material in the plastic zone, because in this plastic zone, it's a lower stress than it would be. So Irwin accounted for this softer material in the plastic zone by defining an effective crack length that's slightly longer than the actual crack size. So he defined the effective crack length is equal to our original crack length plus our radius from the plastic solution. So it's this. So from here to here is our effective crack length. And in the case of plane strain, that makes life a little more complicated because you have stresses in all of your directions that for the case of plane strain, this radius of the plastic zone is 1 over 6 pi times K1 over the yield stress squared, because the additional stress in the through thickness, it allows for some stress relaxation, which means that your stress state isn't quite as high. So this is just a note, if you're looking at a plane strain situation, you have to slightly modify some of the calculations that we're doing. So to make it general for our whatever geometry we look at, because when we talked about the various stress intensity factors, we stuck in this generic Y or gamma term to account for the effects of the various geometries. We had the stress intensity factor equations were different depending on what geometry we had. So we say that the effective stress intensity factor is equal to some correction factor gamma, which is a function of our effective crack length, not our original crack length, times our stress times the square root of pi times the effective crack length. So it's just everything we do. It's not, when we're talking about the plastic zone, it's not the function of the original crack length. It's the function of the function of the effective crack length. There we did that. Okay. And since the effective crack size is taken into account in the geometry correction factor, in real life, when you use the, let's say in the general case, when you look to apply this method, you generally need to use an iterative solution. So first, you compute your stress intensity factor without any plasticity correction. You just do everything based on your original crack size. Then once you do that, you'll get a first order estimate of your effective crack length, because you'll go through everything. You'll compute your R sub y based on your original stress intensity factor. And once you compute your R sub y, you can compute an effective crack length. Then once you do that, you can compute your new stress intensity factor based on all of this, based on this expression. And then, so you keep going through that process and you repeat the process until everything converges. And typically, only 3 to 4 iterations are required for reasonable convergence. Now, in certain cases, you get lucky, and this iterative procedure is unnecessary because a closed form solution is possible. So, for example, for our old friend, the through crack in an infinite plate, we can say that the effective stress intensity factor is equal to the square root stress times the square root of pi a over the square root of 1 minus 1/2 the stress over the yield stress squared. This is for our special case, our most simplified case. And elliptical and semi-elliptical flaws also have approximate closed form practice zone corrections, provided that our flaw size, our A and our C here, are, when we say A, we mean these dimensions, A and C, are reasonably small compared with the plate direction. So for our embedded elliptical flaw, so for this case here, and we have all these equations here, we have this Q correction term and this F of phi correction term. And for the case of the elliptical, we have this lambda correction term. So we have all these correction terms running around in there. But for our elliptical flaw, yeah. So for the case of the elliptical flaw, we can say that our K effective is equal to the sigma times the square root of I times A over Q effective times sine squared E plus A over C squared times cosine squared B. Oh, and this is all to the 1/4 power. So this Q effective, this is taking this equation here and equation here, and this f of phi you see here, this f of phi that we have here, we just modified it. Oops, wrong way. We modified it modified it. We didn't even modify it. We just used that f of p directly. But for the effective Q, we do modify that somewhat, and we say that our effective Q is equal to our original Q minus 0.212 times sigma stress divided by the yield stress quantity squared. So we take the Q we computed here, substitute that in here, and we subtract off this additional factor, and that'll give us our effective Q for our analysis that we can then substitute in here. And also note that for a semi-elliptical flaw, we have this lambda term that we also have to account for as indicated here. So these are just a couple of simplified cases, for closed form cases for specified parameters. And another interpretation of the Irwin plastic zone analysis, plastic zone adjustment, is that of an effective compliance. So if we look at this low displacement, figure here, we have the low displacement behavior of an purely elastic plate, this dotted line here, compared to the low displacement behavior of a cracked plane with a plastic zone at the tip. And obviously, because we have that local yielding and softening, we have a nonlinear response, so we get greater displacement. And so if we apply more and more load, because we have the local yielding and softening, we have a greater displacement. So if we look at the end, we have as I said, at a given load, the displacement of the plate with the plastic zone is greater than that of the elastic plate. And we can also define an effective compliance, which is equal to this maximum displacement for the case of plastic loading divided by the applied stress. We're looking at, mode 1 type of loading. So another way to look at it is our effective crack length can be viewed as the crack length that results in the compliance that you would get that would result in this compliance for a purely elastic material, because we define the because if we do it this way, we just do assume an elastic connection between load equals 0 and load equals P. So That's our effective compliance. Now, like many simplified assumptions, the Irwin plastic zone adjustment is currently not often used for practical applications. It was the first one that was developed to try to account for plastic zone corrections, and it provides some insights into how plastic zones can be accounted for. But it's a baseline. Now, advanced methods have been developed by later researchers, and we'll take our break now, but the strip yield model that we'll talk about after break is what's been taken by a number of researchers and expanded for some more sophisticated calculations of the plastic zone size. So any questions? Okay. So if not, we'll take our break. So we'll pick up again at 25 after. Okay, go ahead and get that started. So, so the Irwin plastic zone correction was the first method developed to account for plastic zone size. Now we're going to move to a slightly more complex model. So the strip yield model was first proposed by Dugdale and Barenblatt. And what they did is they assumed a long, slender plastic zone illustrated in these shaded areas here in a non-hardening material and plane stress. So once again, the assumption is once the stress hits the yield stress, that's it. The stress just remains at the constant yield stress. And these early analysis only considered a through crack in an infinite plate. And the strip yield plastic zone, we assumed that the total crack length was equal to 2A plus 2 rho, as illustrated here, where we have the length of the 2A was the length of the original elastic crack, and 2 rho, and rho was on each side the length of the plastic zone of the crack, and obviously 2 because we have two sides for this configuration. And we assume that a closure stress equal to the yield stress was applied at each. We assume that a closure stress equal to the yield stress is applied at each crack tip. So this model approximates the elastic plastic behavior. We're superimposing two elastic solutions. We have our through clack under remote tension, and then we also have a through crack with closure stresses at the tip. So we take the pure case of the purely elastic solution, then the crack with the closure stresses as a tip, we add them together and we get our total solution. So this is a classical application of the principle of superposition. And since the stresses are finite in the strip yield zone, because we talked about normally our stresses, we talked about this either last week or the week before, the general solution was equal to some constant for a stress was equal to some constant k divided by the square root of the radius times some function of theta plus the summation from m equals 0 to infinity of, am r to the m over 2 gij m of theta. So this was our general equation for the stresses at the crack tip. But for this model, we're saying that the stresses are finite in the strip's yield zone. There can't be a stress singularity at the crack tip. If we can't have a stress singularity, well, we have the square root of r in the denominator here. So this term here has to be equal to 0 in order for this equation to still be valid under the conditions we put on it. And therefore, this plastic zone length rho that we talked about has to be chosen such that the stress intensity factors from our original case where we have just our infinite plate under tensile loading, and we have the crack sitting in the middle. So this case, the stress intensity factor from here has to cancel out with the stress intensity factor from this is if we just had this plate and the only stress applied was this closure stress at the crack tip. So the stress intensity factor from these two cases have to cancel each other out in order for these approximations that we're making to be valid. So how do we determine the stress intensity factor due to the closure stress? So what we do is we consider a normal force P applied at some distance x from the center line of the from the center line of the crack. And we need to look at the stress intensity factor at this crack tip where x is equal to a, and we need to have the stress intensity factor at this crack tip over here where x is equal to negative a. And we're assuming our plates of unit thickness, so we have our mode 1 stress intensity factor at the right end is equal to P over our load divided by the square root of pi times A times the square root of A plus X over A of A minus X. And this is, load divided by area gives us our stress. And our stress intensity factor at minus A is equal to P over the square root of pi times A times A minus X over A plus X. And to do the relation, and here we do the, and we can say that the closure force that we're talking about, this closure force, we can, okay, here's where we relate to stresses. We say that our stress is equal to negative of the yield stress times dx. So our stress times the distance and through thickness plate. So what we do for each of these expressions, we take this A and we replace it with A plus rho, and we replace our load with negative, and negative because it's a closure stress, dx, and we plug all that in, and we sum the contributions from the right and the left. So we take this and add it to this. So we make our substitutions, we plug, we sum everything together, and what we get is our stress intensity factor for our clack closure case is equal to negative of the stress divided by the square root of pi times A plus rho, integral of A to A plus rho. So we're just integrating over the plastic zone, and we're adding, A plus rho plus X, replacing A with A plus rho, A plus rho minus X plus, down here, A plus rho and plus A plus rho minus X over A plus rho plus X dx. And we do simplifications. A plus rho plus X are X plus X and minus X cancel each other out here, and we do some other simplifications, and we take this A plus rho inside the integral. So what we end up with is negative 2 times the yield stress times the square root of A plus rho over A plus rho over pi, integral from A to A plus rho of dx over the square root of a plus rho quantity squared minus x squared. Okay. So what all of this is the stress intensity factor for this case here, where all we have is the closure stresses. Now, and we solve the integral, and we get that our stress intensity factor for our closure stress is equal to -2 times the yield stress square root of a plus rho over pi inverse cosine of a over a plus rho. So this is our stress intensity factor for where the only stresses we have is those closure stresses at the crack tips. Now, what we talked about is this stress intensity factor, in order for this original term here in our expression to go away, this term here we go. This term here has to balance with what our stress intensity factor would be if we just had our plate under infinite loading, no closure stress. So it's just sigma, the square root of pi times a plus rho, where we're replacing a with a plus rho. So we have to set this equal to this, and we have to solve. So what we say is that sigma, the square root of pi a plus rho, is equal to -2 times the yield stress, the square root of a plus rho over pi inverse cosine of a over a plus rho. So, not going to go through the details of the algebra, but what you do is if you take this term, bring it over to the left side, so you take this term, bring it over to this side, and you take the cosine of both sides, and you do some algebra. What you end up with is that a over a plus rho is equal to the cosine of pi times sigma divided by 2 times the yield stress. And this is the condition that has to be met for the relation between A and rho in order for our stresses to not be infinite at the crack tip. Now, one thing to note is that as the stress, if you look at this equation, as the stress approaches the yield stress, sigma over sigma ys gets close to 1. You get cosine of pi over 2, cosine of 90 degrees, which is equal to 0. So this term goes as sigma goes to sigma ys, a over a plus rho has to go to 0. Well, for an arbitrary crack size, the only way that's going to work is that this rho has to go to infinity, because then something divided by a plus infinity is a huge number. So any number divided by a huge number will infinity. Okay. Now we can explore this further by doing a Taylor series expansion. So we take our cosine, and if you learn somewhere along the way in calculus, you can always approximate trigonometric functions with a Taylor series expansion. So we can say that A over A plus rho is equal to 1 minus 1 over 2 factorial, which is just 2, times pi sigma over 2 yield stress squared plus a bunch of other stuff, which the bunch of other stuff is higher order terms that we're going to neglect. So we end up with is just A over A plus rho is equal to 1 minus 1/2 of pi sigma over 2 times the yield stress squared. So we square this, put it under a common denominator, and do some algebra. What we end up with is that rho is equal to pi squared sigma squared times A divided by 8 times the yield stress squared, which is just pi over 8. And remember, our stress intensity factor is just pi times the sigma times the square root of pi a. So we can take sigma the square root of pi a and just say that that's equal to the stress intensity factor. So if we take this and make that simplification, we get that our length of the plastic zone is equal to pi over 8 times the stress intensity factor over the yield stress squared. Now, earlier for the Irwin correction, we said that, so the Irwin correction said that our plastic zone size is equal to 1 over pi times K1 over the yield stress squared. And if you do the math, 1 over pi is equal to 0.318, and pi over 8 is equal to 0.392. Squint your eyes, they're close enough. So you can say that the Irwin and the strip yield approaches predict relatively similar plastic zone sizes. Okay. So, here we go. Now, another game we can play is we can go back to our original definition that says that A over A plus rho is equal to cosine of pi times sigma divided by 2 divided by the yield stress squared. And we can go back and so we can go back and oops. So if we take this take this if we apply this definition, we can take our fundamental definition is that our effective stress is equal to the square root of the pi times A plus rho. And if we and we use this equation to manipulate what A plus rho is equal to, A divided by cosine of this, we can get that our effective stress intensity factor is equal to 0 times the square root of pi times A times the secant, remembering secant's 1 over cosine of pi times sigma divided by 2 sigma ys. And you're solving this, you're solved for the square root of A plus rho, so you solve this for that, and you plug this into here, and that's how you get this. Now, the thing to note that this equation tends to overestimate the effective stress intensity factor. And the actual effective crack length is somewhat less than A plus rho because the strip yield zone is loaded to the yield stress. So Birkeden and Stone obtained through finite element analyses a more realistic estimate of the effective stress intensity factor. So they came up with is equal to the yield stress times the square root of pi A times 8 over pi squared times the natural log of the secant of pi sigma over 2 times the yield stress, all of this to the 1/2 power. So this is just known. And the moral of all of this is that the nice things, particularly in introductory classes, of introducing the simplified means is they're easier to understand than these real complicated, not that these are trivial to understand, but they're still easier to understand than the real complicated methods, than the real complicated methods. And there's still the baseline, the fundamental methods we talk about. When people went on and developed all these more advanced methods of solving problems, it's these initial simplified methods. And again, in many cases they can give a good enough approximation, but they also serve as the baseline of what other people use to develop their new advanced methods. And for those of you go into research, as you go on and develop your own research methods, it's always good to start at the baseline methods and see what improvements you can make from there. So to build on these points a little more, we have this figure here that shows the comparisons between a pure linear elastic fracture mechanics analysis, which is this lower line here, the Irwin correction for plane stress, which is this middle line here, and then the strip yield correction, which is the upper line here. And what we're doing is we're plotting an effective stress intensity factor normalized by the yield stress multiplied by square root of pi A, and we plot it against the normalized yield stress. So the applied stress over the yield stress. Now, the linear elastic fracture mechanics assumption implies a linear relationship between the stress intensity factor and the stress. Once you get above half the yield stress, this is where these plots start to diverge. And it's only when you start getting really close to yield stress. So this sigma over sigma ys of about 0.885, this is the point where you start getting significant variations between the two approaches. So just once you get real close to the yield stress. Now, according to the strip yield model, you see that as you get right up to the yield stress, this starts to become asymptotic because the strip yield model assumes that once you hit the yield stress, your effective stress intensity factor is infinite. The strip yield zone extends across the entire plate and it's reached its maximum load capacity. Now, the plastic zone shape predicted by the strip yield model, particularly at very high stress levels, and we're going to talk more about this in just a sec, doesn't match the actual plastic zones exceedingly accurately. But one interesting little effect is that for polymers for which these methods were never designed, they actually do. So the strip yield model was originally developed to account for yielding in thin steel sheets. But for polymers and some other materials, this method actually works pretty well, which is interesting that sometimes methods work very well for cases for which they were not designed. But even though as is, particularly at very high stresses, it may not do that. It may not do an ideal job. The strip yield model has been the basis of more advanced methods that have been developed for predicting fracture in structural components. So, any questions on this? Okay, so the other thing we're going to talk about is the estimates of the plastic zone size that we've talked about so far only consider the crack plane, where theta equals 0. But we can estimate the extent of plasticity at all angles by an approach. So if we have a multi-axial stress state, we can compute and by superposition summation, that these various stress intensity factors due to the various stresses. So we have our tables here that define for the various and sundry conditions what our stresses are and how they relate to the stress intensity factor in our angles. So at any angle theta, we can say what our multi-axial stress state is. So we get beyond the crack plane, where at some angle theta from the crack plane, we can say what our stresses are at any point rotated from the crack plane. So what we can do then is we can take the von Mises yield criteria, which presume you all have run into at some point, but anyway, the von Mises yield criteria says that yield occurs that when you take this combination of your stresses minus sigma 3 squared plus sigma 2 minus sigma 3 squared 1/2. So if you take your multi-axial stress state, and if this function here, if it's greater than your uniaxial yield stress, you've yielded. If it's less than that, you haven't yielded. But this whole idea of an effective stress, it's all related to the idea that when you do a tensile test in the laboratory, you're just measuring a coupon under uniaxial stresses. But when you're looking at a real structure, it's applied to a multi-axial stress state. So when you have stresses in multiple directions, so the idea of these various yield functions, of which the von Mises criteria is a famous one, is that when, and also here for this way of writing it, sigma 1, sigma 2, and sigma 3 are all principal stresses. Now you can also write a version of this which includes the shear stresses, or as we'll talk about in a minute, that you can relate everything to, you can convert your full multi-axial stress state, including shear stresses, to the principal stress state. But it's the idea is no matter if you have a multi-axial stress state, you can still compute your effective stress and the quote unquote yield stress that you'd apply to these various and sundry methods that we talked about. So for plane stress and plane strain, for plane stress or plane strain situations, the principal stresses can be computed using the equations we talked about before, that we can say that our maximum and minimum principal stresses is equal to sigma xx plus sigma yy divided by 2, plus or minus. The plus is for the maximum stress, sigma 1. The minus is for the negative stress, the minimum stress, sigma 2, over sigma xx minus sigma yy over 2 quantity squared plus tau xy squared, all this to the all this to the 1/2 power. So we can take our full multi-axial stress state computed by these various equations here. We can compute our principal stresses. And note, for plane stress, sigma 3 equals 0. For plane strain, we can say that sigma 3 is equal to nu, the Poisson ratio, times sigma 1 plus sigma 2. So we take all those principal stresses, we plug it in here. That's our effective or yield stress. And we can take all of this and plug it into the expressions that we talked about. So if we take our mode 1 stress fields, and we plug that we take from our table, we plug them into this equation, and we do all the math, we end up with is that sigma 1 is equal to K1 divided by 2 times pi times the radius times cosine theta divided by 2 over 1 plus sine theta over 2. We get sigma 2 is equal to K1 over the square root of 2 pi times the radius cosine theta over 2, 1 minus sine theta divided by 2. And sigma 3 is equal to 0 for the case of plane stress. And for the case of plane strain, it's 2 times the Poisson ratio times K1 divided by 2 times pi times the radius cosine of theta over 2. So theta divided by 2. So this is for the case of plane strain. So we take these expressions and we substitute it into our von Mises criteria. We set the effective stress equal to yield stress, and we solve for the radius because we have the radius running around in here. And what we end up with is we have estimates of the mode 1 plastic zone radius as a function of theta. So for the case of plane stress, we get at our radius as a function of theta is equal to 1 over 4 pi times 1 over, stress intensity factor over the yield stress squared times 1 plus cosine theta plus 3/2 sine theta squared. And for the case of plane strain, we get that our plastic zone radius as a function of theta is equal to 1 over 4 pi times K1 divided by the yield stress squared, 1 minus 2 nu quantity squared, 1 plus cosine theta plus 3/2 sine squared theta. So we can take these equations and we can plot them. So this is what we get for mode 1. This is our plastic zones, our plastic zone for any angle. For the case of mode 1, we have plane stress and plane strain. We can do the same type of thing for mode 2 and mode 3. So this is using our approximations. This is what our plastic zones look like. And note the significant difference in the size and shape of the mode 1 plastic zone for plane stress and plane strain, because as we talked about, plane strain suppresses yielding, so therefore you have a smaller plastic zone. Now these equations aren't exactly right because they're based on a purely elastic analysis, which, as we've talked about, isn't exactly right. And, so it's basically assuming this original idea we had here. And we talked about before that crack tip plasticity causes stress redistribution isn't accounted for in these analyses that we just did. And also the Irwin plasticity correction, which accounts for stress distribution by means of an effective class length we also talked about, is also fairly simple and not totally correct. So here is a figure using a more rigorous way of computing plastic strains, and we'll talk about this later. It's a very simplified method of computing the plastic strain. So the strain divided by some reference strain is equal to the stress divided by a reference stress plus a parameter alpha times sigma over sigma 0 to the nth power. And now this is the plastic zone computed based on this more sophisticated equation of predicting plastic strains. And we're going to talk about this equation later. And also these figures here were computed by the plane strain plastic zone shape with a detailed elastic plastic crack tip solution obtained from a finite element analysis using a more sophisticated equation to compute the stress strain relation. And the only thing to note right now is that this n term relates to the hardening. So the higher that this n value is, closer that your material response is assumed to be for an elastic plastic material. So this elastic plastic material. So this n equals 50 is shown here is pretty close to assuming an elastic plastic material. And another thing to note is that when you use this equation, you don't have a defined yield stress, yield point, because this sigma over sigma 0 plastic strains are assumed to be present at all portions in your loading response. It's just when normally what's called the elastic range, it's just assumed that your plastic strains are very, very small. So for these analyses, the plastic zone boundary was defined as the 0.2% offset yield stress, which is a reminder that if you take your stress point and you take your strain minus your stress divided the modulus. When this is equal to 0.02, that's considered the strain when you hit this point. That's how the stress corresponding to this strain is what you call your yield stress. Now this dotted curve here is what was predicted using the equations we just talked about. The actual plastic zone size is, the size and shape, it's not wildly different, but it is somewhat different. And particularly for the case when we say that the effective stress is equal to the yield stress. Now, when we define the boundary at a slightly lower effective stress, it gets much, much smaller. So much smaller than that predicted by the elastic analysis. So given the difficulties of defining the plastic zone unambiguously with a detailed analysis, these elastic estimates we have for the plastic zone size are actually not that bad. And when we actually say that the effective stress is equal to the yield, 2% yield stress, which is not bad, these comparisons are actually, all things considered, are actually pretty good. And here, and just as an interesting note, which will mean more when we start talking about full plasticity analysis, this figure below illustrates the effect of strain hardening on the plastic zone. So as we allow more and more strain hardening, so more we move away from this and allow our stress strain curve to get, stiffer and stiffer, even in the plastic zone, since it can carry more stresses and therefore there's less stress distribution, which means that the plastic zone size is smaller. So all these things are just a function of what we assume the stress strain response will be. So for materials where we can assume that it's pretty close to an elastic plastic, just our very simplified analyses give a pretty good estimate, but just note that if you have a material with a significant amount of strain hardening, which we didn't account for at all in our analyses, that our estimates of the plastic zone size may be overestimated. So, any questions on any of this? Okay. Not, that's it for today. And a reminder, because particularly some of you signed in late, we did reminder homework 2 is due next week. And the first midterm, well, the midterm will be 2 weeks from today in class, and it'll cover homework 1 and homework 2. So no more questions on anything. Have a good week, and I'll see you folks next week.